at this question, which is how do we fill in this summary table or make it a resistor. Let us now recall the formula to relate the resistance R, in this case R, to three variables. So in this case, the three variables are actually my rho. Okay, rho stands for resistivity of the material used. Okay, in this case it can be copper, silver, or even gold. Okay, so this is a constant number, and there's another variable called L. Okay, L represents the length of the material used. It can be even a length of a wire. And the last variable, which is very important, is actually the cross-sectional area of the material, or the cross-sectional area of the wire. So this is a very important relationship you need to use to solve the following question, to fill in the table below. So let us look at the information given. Okay, the L is given as 1 meter. Okay, area is given as 1 meter squared, and using same material means my rho will. So once you see this, so you can see my rho is actually a constant, so it won't change. Okay, and my original resistance is actually only 10 ohm based on 1 meter squared and 1 meter. So let us now move on to look at the rest of the table. Okay, so what are we supposed to fill in this table? Let's focus on row 1. So in this case, okay, row 1 is saying that we need to identify whether which variable is kept the same. As you can compare with the information on the top and bottom, the length and the cross-sectional area remains the same. So in this case, I'll fill in L, comma A. Okay, and the resistance is still 10 ohm. Okay, so this first part is now filled in. Let's move on to the second part. So in this case, the L remains the same, which is still the cross-sectional area remains the same, which is 1 meter squared. So I just put in as A remains the same. So what has actually changed if you compare with row 1 is the length. So in this case, my 1 meter has now twice, so it's actually times 2. So when length times 2, because resistance is directly proportional to L, as you can see from the information, the relationship above. Okay, so in this case, my 10 ohm original resistance will have to be multiplied by 2. Therefore, my answer is 20 ohm. Okay, let us now move on to the third row. In this case, my cross-sectional area still remains the same, so I fill it as A. But if you look carefully at my length, it has now reduced by half. So it's actually times half. So in this case, when it times half, my new resistance will be actually 10 times half. So in this case, my answer is 5 ohm. Okay, so let us move on to the fourth row. Okay, so what remains the same is actually my length. So I just fill in, it's still 1 meter compared to 1 meter, and the only thing that changed is actually my cross-sectional area. If you compare with the original area, it has actually 1 meter squared is actually times 2. But if you can recall the relationship relating resistance to cross-sectional area A just now, look at it again. It's actually a inverse relationship. So in this case, when it's actually times 2, my new resistance is actually times half and not 2. So in this case, my resistance is still 5 ohm. So let's move to the last one. Okay, my cross-sectional area has actually becomes half, so it's actually 1 meter squared times half. So in this case, because of the inverse relationship, my 10 must still times 2 because of the inverse relationship. So my resistance has actually increased to 20 ohm. Okay, so that's all for the explanation relating to this relationship here.